Hi everybody, today we're starting projectile motion. A projectile motion is any object that moves through airspace acted upon only by gravity. And we'll mention air resistance again, though we typically don't do much with that in AP Physics 1. Here's a cannonball being launched horizontally off the edge of a cliff. And already last chapter we talked about gravity. Gravity accelerates things in the vertical direction at 10 meters per second each second. And if you look here, v sub y stands for the vertical component or part of its velocity. And notice that the cannonball's vertical velocity, represented by this vertical vector, gets larger and larger by 10 meters per second every second. But here's the interesting part. V sub x stands for the horizontal component or part of its velocity. And if you look at it, look at the horizontal vector. It actually keeps the same magnitude as the cannonball flies. And this, believe it or not, is the big idea in this chapter. But before we get into projectile motion, I want to quickly digress into vectors. Now, I know many of you did vectors probably in math class, but not all of you. So forgive me as I digress or sort of sidebar into this. Oh. Sorry, most of you probably played Angry Birds at some point. Why was Angry Birds so cool besides the music and the graphics? Its projectile motion was actually modeled on real physics equations. And so all of it was actually legitimate. I don't want to spend too much time with it. Just a quick reminder, a vector quantity includes both magnitude, a size, and a direction, which way it's pointing. Whereas a scalar quantity only has magnitude or size, but no direction. Some quick examples here, and I'm going to go through it real quick. Mass is a scalar quantity, doesn't have a direction. Volume of water, liters, is a scalar. Time, again, we talked a little bit about this, is usually treated as a scalar because we cannot easily change its direction or its rate. Anatomy of a vector, most of you know this already. The tippy pointy part of it is called the head. The back part of it is called the tail. And the length of it is proportional to the magnitude. So if you had two vectors, one which was 3 meters long, and you had another vector also pointing east that was 6 meters long, the 6 meter long one should be twice as long. I'm not sure if I actually drew that very well, but you get the idea. So a little bit of practice with the magnitude and direction. So you've got 8 vectors shown on this grid. List all the vectors that have the same magnitude as vector A. Now when we're talking about magnitude, we're talking about the length of it. And if you look at vector A up here, it's 3 units long. So what other vectors are 3 units long? And you probably fairly quickly notice that would be both D and G. And just take a quick look at it. D over here is exactly 3 units long. And G is also 3 units long. And so both of them have the same magnitude, but not necessarily the same direction as A. And then finally, B lists all the vectors that have the same magnitude as vector B. B is 5 units long. So I'll give you a second, look around here. Which other vectors have a magnitude of 5? And the answer is, yeah, if you haven't guessed it, there aren't any. It was a trick question. None of them have that same magnitude. All right, you're like, okay, magnitude's not so bad. Well, what about direction? A lists all the vectors that have the same direction as x. Well, if you look at x, it goes down 1 when it goes over 1. Whoops. Which means it's kind of got a slope of -1. So what other vectors here have that same direction or is pointing downward 45 degrees? And the answer is you should discover that both are B, E, and H are all heading in that same direction. They all go down 1 and over 1. So they're also pointing downward at that 45-degree angle. And you're like, okay, easy enough. This next question, though, is a little bit trickier. List all the vectors that have the same direction as the vector negative x. And you might say, whoa, 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 what is negative x? Well, we've worked with numbers before. If you've got 5, what's the negative of 5? Well, negative 5. How do you make a negative of a vector? Well, when you do a negative vector, it has to have the same magnitude, but the opposite direction. So right here, this is negative x. It's got the exact same magnitude as x, but it's pointing in exactly the opposite direction. So now the question is, which ones have the same direction as this vector? And if you check here, you can find a few of them. Vector x, by the way, is now going up 1 for every 1 unit that it goes to the left. And you'll discover that, oh yeah, both A and C are both going to, or having that same direction. Its head is pointing in the same direction as the head of negative x. How do you add vectors? Well, when you add numbers, you just get the sum. We have a fancy name for the sum of vectors. It's called the resultant. And the resultant is the sum of 2 or more vectors. How do you find it? Well, it turns out if you want to add A plus B, sorry, pause for a second for those of you whose brains, whoa, I can't draw right now. It doesn't matter the order you add vectors, just like it doesn't matter which order you add numbers. 2 plus 3 is the same as 3 plus 2. The same is true down here. What's the sum of vector A and B? Well, you can either add A to B or B to A. But here's the rule. When you add vectors, the head of one vector must meet the tail of the other vector. And you can't change either the magnitude or direction of either vector. So you can draw A here first, and then put B at the end of it, the tail of B to the end of it. Or you could put B down first and then put the tail of A. The resultant of these two vectors, or the sum, goes from the tail of the first all the way to the head of the second vector you draw. So in this case, here, or this purple vector, is A plus B. And you'll get it either by adding B plus A or A plus B. So, what's the resultant or sum of these two vectors? And you might say, oh, it's easy. It's a vector that points, just from here over to here or from here to here. Unfortunately, that's not the way you add vectors. You always add vectors head to tail. And right now, these are drawn tail to tail. So what's our options? Well, we can either take this vector and move it over to here, and now its tail matches up with the head of the other vector, or you can take this vector down here and move it up to the top here. Remember, this is associative. You can add it in either order. Now its tail is at the head of the other vector. What's the resultant of this? Well, the answer is this red vector right here that points from the tail of the first vector we're adding to the head of the last vector we're adding. Officially, I guess the red vector should be a little bit longer. And if you're like, whoa, I don't get the whole idea. Well, think about it this way. Say you started out here and you walked north and then you walked east. Where are you relative to where you started? Well, you're along this red vector. The displacement you had would just be this vector right here that points from your starting position to your ending position. And it doesn't matter if you walk east first and then north, or north and then east, you'd still end up in this final position. We also sometimes have to work backwards. You have to take a single vector and break it into two component vectors at right angles that would add to that original vector. This is called resolving a vector into its components. And we'll take a look at it here with some examples. If you had this vector, say for example you walked northeast in this direction, how could you figure out how far north and how far east you actually walked? Well, you could actually break this one and say, all right, I walked east that far, and then I walked north this far, and that got me to this final point right here, from my starting point down here. You might say, wait a second, could I have gone vertically first? Yeah, you could have also gone this way first, this far north, and then from there, this far east. Forgive my non-straight numbers or lines or vectors. But yeah, either way. And now these two vectors, the horizontal and the vertical ones, would add to this. And you might say, well, wait, why are we even doing this? I'll give you a hint. It has something to do with projectile motion. And if you remember the first slide, the horizontal component of the velocity doesn't change, but the vertical component does. So what are we going to have to do in this chapter? Well, every so often we're going to have to break a velocity into its vertical and horizontal components, like we just did here. I'm going to help you with one of your worksheets. This is one of your homework ones for tonight. For the top 4 vector combinations, you're just adding them. The problem is, again, is they're drawn tail to tail, so you've got to actually move one or either one of the vectors. So, for example, in the first one there, I could take that vector and move it over here to this side. Or I could have taken this vector and moved it up there. In either case, though, the resultant points from the tail of the first vector I'm adding to the head of the last vector I'm adding. So in this case, it would be this purple vector pointing from the starting point to the ending point. And that would be my resultant. You can figure out the other two. Let me do the last one, though. It's a little bit tricky. So you could either take this vector and move it over to the end of this one. I think it's a little short, actually. Or you could take this vector and move it up to here. Forgive me for my lack of good idea here. But and you end up the resultant here. You might notice that no matter how you do this, if you move both vectors, you'll end up forming a parallelogram. In fact, adding vectors this way is sometimes called the parallelogram rule, where you complete the parallelogram and the resultant then points from the corner where the vectors are starting to the corner where the vectors end. Down the bottom part here, we're working in reverse. We're going to take these vectors and break them into their vertical and horizontal components. Well, if you look at the first one here, we can draw a little dotted line downward, and that means its horizontal component would be that. And if I do the same thing with its vertical part, its vertical component would be something like that. Doesn't matter where you draw them. In this case, they want you to sort of draw them on the axes. And again, let me do the fourth one for you. The fourth one here, there's its horizontal piece. And for the vertical, they didn't give us an axis. Kind of tricky on their part. So you just have to draw it like that. You might need a straight edge to do this one. Please, 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 as you're drawing these, make sure that they remain parallel to the vector or the original vector as you move them. And they should have exactly the same length, unlike my animations where I couldn't quite get them quite right, even after tweaking them. It's also possible to find something that's a little bit more interesting. If you're adding 3 vectors, in this case, let's say you had 10 meters north, then 6 meters east, then 4 meters south. Where do you end up? Well, you end up along this resultant. This is the sum of those 3 vectors. And my question is, what is that length of that vector? And at this point, you're like, wait. I don't think we ever did this in geometry. You probably haven't. But there's a trick to this, and some of you might have already seen it. I'm hoping you can kind of look at this and go, wait, I can figure out the length of that vector. Well, if you take a look at it, oh, actually, I didn't do this one. Okay, let's do it together. Sorry. So what can you do in this case? Well, we actually know the horizontal component of this red vector. Why? We just ended up 6 meters to the east of where we started. That's all we walked over here. How far north did we end up from where we started? Well, we walked 10 meters north, then 4 meters south, not to scale. My vector's not quite the right length, which means this one over here has to be 6 meters as well. This is a right angle. And so that means we can actually quick use Pythagorean theorem. 6 squared plus 6 squared equals the hypotenuse squared, which in this case, can I just do without doing a decimal? Most of you know your 45 90s, which means the hypotenuse is going to be 6 root 2 meters long. And by the way, yes, you could also figure out the angle of that resultant, theta. We already know in this case it's 45 degrees, but you could use trig to find that angle as well. So what about the second one? Let's take a look at this one. What if you walk 10 meters north, 10 meters east, then an additional 5 meters north, then 3 meters west? Well, you'd end up this far from where you started. And again, some of you are like, wait, how do you figure out that length and that angle? You could very quickly figure it out. Forgive my lack of a straight line. We could figure out the vertical and horizontal components of our resultant. Again, right angle to each other, even though it may not look like I did it. How far north do we end up from where we start? Well, we go 10 meters north and 5 meters north, a total of 15 meters north. And then what about this? How about the horizontal? Well, we walk 10 meters to the east and then 3 meters to the west, meaning we should end up 7 meters to the east of where we started. So how do we figure out the resultant in this case? It's going to be the square root of, just using Pythagorean theorem, 7 squared plus 15 squared. And I don't have a calculator handy, but you could very quickly solve it. Oh wait, actually I do know this one. I think it's about 14. No, it can't be 14, sorry. Whatever it is. And you could also figure out the angle. How do you figure out the angle? Now it's probably worthwhile talking about theta. Probably the easiest way, once you figure out the hypotenuse, you could use that. But otherwise, tangent, again, remember, is opposite over adjacent. So you could very quickly set up on your calculator. It would be 15 meters over 7 meters. And if you did an inverse tangent of 15 over 7, you could find theta. All right. What about these? What if I drew them separately? Well, all you would have to do for this one is simply put them end to end. And if you haven't seen it already, I'll give you a hint. We could move this 10-meter one down here. And then I could move the 5-meter over here. Again, head to tail. And then I could move the 3-meter over here. And if you haven't already seen it, again, drawn not to scale. I didn't have time to actually measure out each one. This is the same as the previous problem. And believe it or not, the answer is the same. Does it matter what order you add these together? The answer is not at all. So you can solve it. All right. I want us to try this real quick, and don't panic. You've got 3 vectors labeled P, Q, and R up above here. And down below here, we're just going to write some mathematical expressions for adding those vectors to produce the vectors shown. So for example, if you look at this first one over here, what is this vector right here? Well, this vector here is P. Notice it has the exact same magnitude and exact same direction as vector p up on top. What's this vector right here? Well, that is q, in the same direction and magnitude as it up here. So what do we know here? X, the resultant, is just the sum of p plus q. And you're like, okay, this is easy. All right, so let's try A real quick. Well, you might recognize right away that this is vector p. But wait a second. What's this other vector we're adding together to that to get vector A? Well, if you look at it carefully, it has the same magnitude as r. It's just pointing in the negative direction. What is this vector? It's negative r. And so how do you get A? It's just p plus, or I guess I could just write it, plus negative r, or just minus r. And you can try a couple of the other ones real quick, but let's do E real quick. What is E? Well, if you look at this vector here, you should recognize that's negative p. And then what's this other vector over here that we're adding to it, adding to p to get E? You should recognize, oh, that's negative q. It's the same magnitude as q, but in the opposite direction. So how do we get E? It's negative p minus or plus, either plus negative q or minus q, either one is fine, minus q. Hopefully that feels pretty comfortable. Oh, I've got a brain break here. It's a mathematical brain break. Using only the paths and directions shown, how many routes are there from point P to point Q? Now the arrows on here kind of give you the direction. So you can go this way and this way and this way and this way and this way to get to Q. You can also go down, down, down and go this way, but you can't go backwards. So for example, if you, let's see, went this way, you couldn't go down this way. You'd have to go this way and then this way. But if you go that way, you actually get trapped here because you can't go this way and you can't go down. So I'll let you try this real quick. If you want to, you can pause the video and try to figure out how many paths there are from P to Q that are legal. All right, 3, 2, 1. Here's the answer. There are 7 routes. And you might say, whoa, you could do it by trial and error, but you can also do it more methodically. You can figure out and the number of possible paths you can take to get to that particular junction. And you'll discover there are 7 paths, for example, to get down to this point here. 5 from this direction, 2 from this direction. And there's 0 coming down from this one. And so there's only 7 possible paths down here. Anyway, it's kind of fun. You can do it, but yeah, it's kind of a neat one. All right. We've been adding displacement vectors, but you can also add velocity vectors. In fact, you can add any type of vectors you'd like. And I want to talk about velocity vectors because I already gave you the hint. We're going to be dealing with velocity vectors in this unit. Take a quick look at this. If you've ever been flying on a plane, they have if they have the little monitors on back, one of them is the flight statistics, and it'll show you your airspeed, wind speed, and your ground speed. And you might say, wait, why are there so many different numbers? Yeah, they'll list the airspeed as either a tailwind or a headwind. Tailwind means it's coming from behind you, headwind coming from the front towards the front of the plane. And so, for example, if you're on a plane that can normally fly 80 kilometers per hour, that's its airspeed, the speed it can normally fly through the air. But if you've got a tailwind of 20 kilometers per hour, your plane will actually fly at 100 kilometers per hour relative to the ground. Why? Because the plane can already fly 80 kilometers per hour and the wind is blowing from the tail. You got a tailwind of 20 kilometers per hour. Those two velocities add, and now your plane can fly faster relative to the ground. Also, you can also have this problem. if you've got a headwind of 20 kilometers per hour, now, and I moved this, I know officially I should have the 20 right on top of the 80, but I moved over to the side just to make it a little bit easier to see. If you have a headwind of 20 kilometers per hour, now you're only moving relative to the ground at 60 kilometers per hour. Your ground speed is 60. Why? You're fighting the wind the entire time. So here's a quick conceptual question. We've done headwinds and tailwinds, but what if you've got a wind that's coming at a right angle? Will it make the airplane fly faster or slower than 80 kilometers relative to the ground? Will it make the ground speed more or less than that? And if you haven't figured it out already, the answer is it'll increase it and blow it off course by a predictable amount. So take a look at this real quick. I drew these, unfortunately, tail to tail, but you can kind of get the idea. If you complete the parallelogram, if you had a 60 kilometer per hour crosswind, you'd end up with a resultant of 100 kilometers per hour, but at a really horrible angle. It would be about 53 degrees north of east from this kind of perspective. It would take you off course, but you could be going faster. Talking about vectors here real quick, that was a 3, 4, 5. Most of you remember how to add those vectors. 3, 4, 5 is one of those perfect ones. 3 squared plus 4 squared equals 5 squared. But the angle there is about 37 degrees if you had to figure it out. And the other side is 53, which is why I could say it was 53 in the previous plane problem. And again, remember your 45 degree ones. There, if the two legs are 1 and 1, the hypotenuse will be root 2 times larger. You saw that earlier when we did that one problem. And the angle there, 45 degrees. So why am I bringing this up? Well, you can also add vectors that aren't already perpendicular. So for example, in this case, what if you walk 10 meters northeast and then 5 meters north? How far from your starting point do you end up? And you might say, oh, wait, we learned this. You can do this with law of sines or law of cosines. You could, if you remember those functions. Some of you are like, wait, I never learned these. It's okay. But if you look at my hint up here, you can actually solve this by finding the vertical and horizontal components. If we take the 10-meter vector and break it into its vertical and horizontal parts, we can use some trig, and actually I'm going to do this decimal-wise. Yes, I know it'd be 10 over root 2, or you could do all kinds of things, 5 root 2. But I'll just write it as a decimal, 7.1 meters. And you're saying, well, wait, what if the angle wasn't so nice? Well, yeah, it turns out, since it's a right triangle, the sine of 45 degrees is equal to the opposite side. I called it y in this case, over the hypotenuse, 10 meters. And if you solve this, you'd get that 7.1. And then for the adjacent side, I call that x. Cosine of 45 degrees would equal x over 10. In this case, sine of 45 and cosine are the same thing, so it's kind of trivial. You might say, okay, well, how does that help us? Well, it means now we can actually figure out the hypotenuse. Horizontally, I end up 7.1 meters east of where I started, and vertically, I end up 12.1 meters north of where I started, 7.1 plus the 5. If you do Pythagorean theorem, my resultant is almost exactly 14 meters. And yes, you could even figure out the angle down here at the bottom by doing a little bit of trig. So if you want to figure out the angle that this is going at, you could just do tangent of theta. In this case, would be equal to, and I'm going to leave off units just for speed, 12.1, the opposite side, over the adjacent side, 7.1. Oops, forgot my theta. And you could solve for the angle then that this resultant is pointing. What if you had more than just two vectors? Well, you can just go ahead and break them all into components. In this case, k, which is not shown, is the sum of vector A, B, C, and D. And you might say, whoa, 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 how in the world can we figure out the horizontal component of K when it's not even shown? Well, since we know K is just the sum of these, we can actually just look at the x components of each one of these four vectors. So for example, the x component of A is -2. The x component of B is +2. The x component of C is -1. And the x component of D is +3, giving us that. And yes, you could do the same thing with the x components. And I did it real quick here just so you can sort of see it. A is +3, B is -2, C doesn't have 1, and D is 1, meaning the sum of the components there must be that. What can we do now? Well, we know that those are the x and y components. The purple vector there is actually vector k. And yeah, you could figure out both its magnitude, which will be 2√2, and the angle, which will be 45 degrees. I won't do this next one, but you would do it in the exact same way. Let's take a look at this next page. In this case, it gets a little bit more complex. J is the sum of those four vectors shown. How in the world would you figure out the direction of J? Well, you might have gotten a hint already from the previous slide. What am I going to do? I'm first going to go ahead and figure out the horizontal components of J by taking the horizontal components of N, P, Q, and R. Horizontal component of N is 3. For P, well, I did them backwards. I did R next, -2. Q is -1. Oh, sorry. Wait a second. Oh, sorry. Oh, no. It was right. Sorry. N is 3. P is -2. Q is -1. And R is +2, giving us 2. Again, X here stands for the horizontal part, X direction. And then we do the same thing for the Y. Y components, N is 1. P is 3. Q doesn't have 1, and R is -2, giving us again 2, meaning we have a nice, again, right triangle. And yeah, we already talked about this. It's the same as the other one. So what's the direction? Well, if we do the tangent 2/2, you get 45 degrees. Finally, I'll show you this other one. Here they didn't even draw them all from the origin, so you got to think a little bit. If you do this one, you'll get K. So P is, P is -Q. Wait, oh, no. This is, wait, did I screw up? I think I did. Let's take a look at the other one real quick here. So Y direction, P is 1. I did not fix this one. All right, let's do it real quick together. So, I see, I copied these over without changing the numbers. No! So solving this one real quick. So for the horizontal directions, -2, +2, 0, -1, +3. Okay, that is 2. Even though the numbers are wrong here, up on top. Ignore the numbers. What about the Y part? Well, this is 3. That's -2. So we're at 1. This one doesn't have any. And then this one is 1. Again, even though my numbers are wrong, the resultant is correct. It's 2 and 2. So again, yeah, it's going to be 45 degrees. You can end up with other angles. It's just these two happen to be both 45 degrees. Not nearly as fun. All right, this one I love. It's a thought question. Two vectors each have a magnitude of 6 units, and each makes a small angle. The fact that it's a small angle, alpha, is important. 4 students are discussing the resultant vector obtained by adding these two vectors. Amanda says, since these are vectors, we need to use Pythagorean theorem. Oh, by the way, both of them have a length of 6. you just use Pythagorean theorem to find the magnitude. In this case, the magnitude would be the square root of 72. The direction will be downward. So 6 squared plus 6 squared equals 72, so you just take the square root. Bella says, since these are vectors, we have to find a magnitude and a direction. We use the vectors to determine the direction, which is down, but to get the magnitude, we just add the individual magnitudes. The resultant is 12. Conrad says, I think the direction is actually up. The resultant should add to these vectors to get 0, and since these two point down, we need another vector pointing up. Donald says, the magnitude will be less than 6. Each of these points down just a little, so the resultant will be pretty small. Which, if any of these students, do you agree? And you can choose none of them. I'll let you think. Pause the video if you'd like. I'll give you a countdown before we give you the answers. In 3, 2, 1. Correct answer, and you can argue this one a little bit, is probably Donald. Why? Well, if you break these into their vertical and horizontal components, what's going to happen to the horizontal components of these two vectors? They're equal and opposite. Same angle, same magnitude. These two have to be the same. So these two vectors are going to add up to produce a resultant of 0. Now, as long as, and you need a little bit of trig here, as long as alpha, angle alpha, is less than 30 degrees, what's going to happen? Well, as long as alpha is less than 30 degrees, these two sides are going to be less than 3. And because it's a small angle, I'm assuming they meant really small, like 10 or less. So in that case, since these two sides, if it was 30 degrees, this side would be 3. But if it's less than 30, these have to be less than 3. So adding them up, then it would be less than 6. And it would be pointing straight downward. All right. So I think I'm agreeing with Donald. If you said none of them because you didn't know whether the angle was less than 30, that would also be a valid option. All right. Talking about angles real quick, oftentimes we'll use the compass rose to sort of describe it. Say, for example, you went 100 kilometers in this direction. It's not exactly east, it's not exactly north, it's not northeast, because northeast would be exactly 45 degrees between these two. How would you describe it? Well, there's two ways of describing this. One way would be describing it as 30 degrees north of east. So it's 100 kilometers, 30 degrees towards the north from directly east. What's the other way you could describe it? Well, you could describe it as 60 degrees east of directly north. Either one of these is perfectly fine, but we'll oftentimes use it. Yes, you could also just use, from geometry, you could simply say, hey, it's at 30 degrees, and we'd probably get it. But we tend to be pretty careful about this because, for example, if you know bearings, if you're an airline pilot or sailing boats, you know that north is actually considered 0 degrees, unlike geometry. East is 90. South is 180 degrees. And west, of course, is 270, which if I ever get a chance, my pen is being very slow. And so if you just listen angle, people can get confused because they're not sure if you're using bearings, if you're using geometry, or some other numbering system. And so we tend to try to do one of these other ones. This is one homework problem real quick. How would you find the resultant R? And I just want to sort of talk you through this one real quick. How would you do it? Anytime you have a vector that's not already horizontal or vertical, we break them into their components. Where did I get these two numbers? Just using trig. 175 times a sine of 30 degrees to get this side, and 175 times the cosine to get that side. And the same thing up here, you could break those into its components. How did I get these? 150 times the cosine of 20 to get this side, and times the sine of 20 to get that side. Once we have that, you can actually solve it. What's the net motion horizontally? Well, 89.7. That's the sum of this piece, and this piece. And you can also figure out the vertical part, whoops, went the wrong way, is 228 meters, just the sum of the two vertical ones. And so you could find the resultant here and the angle that it's acting at. What would that angle be expressed at? Well, probably 68.9 degrees north of west, north of directly west, because we'd have to head this way over, north from west. All right. I'm going to skip this one, but it's the same idea. And we're going to do the vector addition program after I get back. So don't worry about it right now. We're going to actually do some quick vector addition stuff graphically with your programming language. All right. Last piece I want to get into just real quick so you can sort of see how this all fits together. This girl just threw a ball at an angle. Well, we can break that velocity into the vertical and horizontal components. If you take a look at it, say, for example, she threw it at 50 meters per second at an angle of 53 degrees, where this is 53 degrees above the horizontal. How in the world would you solve this thing? Well, yeah, just use a little bit of trig. To find the horizontal piece, the adjacent side, it's going to be equal to the adjacent side, which I'm calling v sub x, velocity in the horizontal direction, over the hypotenuse, which is 50. And if you just rearrange that, 50 times the cosine of 53 degrees gives us, whoops, I drew right on top of that, gives us our magnitude, let me erase my angle, of 30 meters per second. Likewise, on the other side, we can use trig again, and I'm going to call this v sub y for the vertical component of the velocity. And you'll discover, okay, that's going to be about 40 meters per second. What's the big idea? Well, if you remember from the first slide, this horizontal velocity remains constant. So what is it at the top of the path? It's still 30 meters per second. And what is it at point C? Also 30 meters per second. It doesn't change even as it flies. That's one of the big ideas in this chapter. But what happens to the vertical part? Well, if you think about it real quick, just to make things easy, let's say g is negative 10 meters per second squared. That means it's going to decrease by 10 meters per second every second it's moving upward, and then increase by 10 every second it's moving downward. Initially, it's going at 40 meters per second vertically. When it reaches the top here, there is no vertical component of velocity. It stopped going up. Could you please tell me the time this would happen? Well, if you work it out, after going up 1 second, it'd be going 30 meters per second vertically and 30 meters horizontally. After 2 seconds up, it'd be going 30 meters horizontally. That stays the same, but only 20 up. After 3 seconds, it'd only be going 10 meters per second upward, and still the 30 meters per second that way. So yeah, if you haven't quite worked it out yet, when would it get to the top of its path? At 4 seconds. At that moment, this vertical component of the velocity would drop to 0. The horizontal, though, stays the same. And then if you haven't figured out already, when would it return to the exact same spot or height it was starting? The answer is it should be about 8 seconds. And if you worked it out, that's 4 seconds after it reached the top. What would be its vertical component of velocity at that instant? Pretend that's a straight line. It should be 40 meters per second, but now downward. After falling for 4 seconds from the top and gaining 10 meters per second each second, it would now be going that. What's its resultant velocity? The sum of those two would give you, yeah, if you did it again, would give you that 50 meters per second it started out with. What angle is it traveling at? It's traveling at 53 degrees below the horizontal. All right, we'll come back and pick this up next time. Have a great night. You've got a couple of worksheets for homework tonight, nothing too terrible. And you've got a video segment to watch about falling objects as well, but nothing too terrible. Also, don't forget to start working on test corrections if you haven't. Hopefully I left the tests there. Have a great night, and I will see you soon. Bye-bye.